Yes, and then now let's prove to this corollary. First of all, it's okay. If R matrix is n by n and also determinant of A non-zero, it's okay. So our matrix is invertible, and also this one, the formula, and the to find the inverse matrix is okay. And we know the previous and the theorem here. This one is okay. Take this one, for example, take this one and this one. It's okay here. And then if A is not zero, determinant of A not zero, this one is scalar, so multiply by 1 over determinant of A is okay, and both sides, this one. So left side, this one is okay, yes. And also we know that, and the adjoint, we know that 1 over A is a scalar, and using this property, A is a matrix, this one is a matrix, multiplied by this one, we can rewrite, and the scalar here, A times adjoint matrix, it's okay, this one. And also, we know that, and the adjoint matrix is A times adjoint matrix, this one is okay, identity matrix times and this scalar, it's okay. So, and we obtain and cancel this one and this one, identity matrix, it's okay. So, and left side, this one, right side, identity matrix. So we know the inverse should be unique. A times this one is the n matrix is equal identity matrix. So this one will be the inverse matrix. It's okay. If we have the A times B is B times A is identity matrix. So, and using the this fact, and the inverse matrix is unique, so, and the B should be inverse matrix. It's okay. Here B is this one, is a matrix. Okay, this matrix. So, and this matrix is the inverse of the A. It's okay. So, and this one is the theorem. It's important theorem. If, and how to check that this theorem gives the method how to check that any matrix is invertible or not. It's okay. Only, and not find the inverse matrix if invertible. If our matrix is invertible and determinant not zero. If determinant not zero, our matrix is invertible. If and only if condition is this one. It's okay. So this one gives the method. So, and take the n matrix. It's okay. If, for example, determinant of a 4. So we don't know the entry of A. It's okay. For example, this one 4 by 4, or we know. So, and the question is, our matrix is invertible or not? You don't have to compute the inverse. It's okay, method. We know that this theorem, if and this one is 4, so, and not 0, 4, so there exists the inverse. Our matrix invertible. It's okay. And then, if our question find the inverse, yes, use and the previous this method adjoint by using the adjoint matrix, or using the elementary row operation and the first method, and then we get the inverse matrix. It's okay, inverse matrix. So, and we obtained this result, the corollary of the this theorem. It's okay if R matrix n by n matrix, and look at this homogeneous system. Right hand side 0, so this one is homogeneous system. We know the homogeneous system always solution. 0 is a solution because 8 times 0 is 0. So x is 0, always solution. This solution is called, we know that from the last lecture, trivial solution. But our aim, of course, if there exists and they find the non-trivial solution, and the question, and our homogeneous solution, homogeneous equation has non-trivial solutions or not. So, and this corollary gives the method, is okay. So, if the homogeneous system has a non-trivial solution if and only if determinant 0. And means how to check that and the design is non-trivial solution or not. You don't have to solve this system. It's okay. Only check the take the coefficient matrix A, compute the determinant. If determinant not 0 and means has only trivial solution. If 0, so we got non-trivial solutions. Is okay? And this theorem is corollary. It's important. It's okay? So let's give an example. It's okay. But look at the come back the corollary. Be careful. Design is should be n by n matrix. Design is square. Otherwise, these and the corollary is not valid. Be careful. It's okay? Because coefficient matrix not n by n, for example n by n, so what's the determinant? Determinant undefined is okay. Determinant, and we can define the determinant of A if our matrix is square matrix. If the coefficient matrix not square, so it is not possible to mention the determinant of A. It's okay, be careful. This one is this corollary is valid only coefficient matrix, square matrix. Is okay. So let A be 4 by 4 matrix. Is okay. If determinant -2. Is okay. First question. Describe the set of all solutions to the homogeneous system AX is 0. It's okay. And the next one, if A is transformed to the reduced row echelon form, this form is B. What is this matrix B? It's okay. So, and the next one, give an expression for a solution of the linear system AX B. But here and not right and B is here. This one is B, and also the previous question contains B. And this one is C, for example. What's the C? It's okay, C. The next one, AXB, right hand side. It's okay. So this one is B. Give an expression for a solution. Sorry, there is a problem here. Wait, please. Yes. This one is C, matrix C. What's the C? This one is B. This one is B. Yes. Yes. What can you say about the first one? Describe the set of all solution of the homogeneous system. We know that every homogeneous system has trivial solution. And they describe the set of all solutions and means, and if there exists, and check that there exists a non-trivial solution or not. It's okay. And so if we get the non-trivial solution, so what's the form of these solutions? It's okay, solutions. And here, determinant of A non-zero. Determinant of A non-zero. So this one is non-zero. So, and using this one, A is square matrix, use and the previous corollary is this system has a non-trivial solution. Determinant of A 0. It's okay, but this one is non-zero and means we get only trivial solution. It's okay. So this system, determinant not zero, so this system, homogeneous system, has only trivial solution. This system has only trivial solution. What's the reason? Because determinant of A minus 2 not 0, use the corollary. It's okay. Corollary. So the next one, if A is transformed to the reduced row echelon form C, and means start with A, apply the sum operation, we get the matrix C. C is the reduced row echelon form. What's the C? C. We know that, and if and the A is determinant of, we know that determinant of A not 0, so means A is invertible, non-singular. There exists inverse. There exists inverse means A is using the sum elementary row operation. A can be transformed to the identity matrix. It's okay, identity matrix. Because what's the reason? And the first method to find the inverse matrix, write the A and write the identity matrix. It's okay. So use the elementary row operation. We know that determinant of A non-zero, so this matrix is invertible. Invertible so means we get the reduced row echelon form, and this one should be identity, this one should be inverse matrix. It's okay because there exists the inverse. So means, and we get, and this one means A is row equivalent to identity matrix. It's okay because A is invertible. So what's the matrix C? C is, yes, identity matrix. It's okay. So A transformed to the reduced of echelon form C. What's the C? C should be identity matrix, because what's the reason? Because A is invertible matrix, because determinant not 0. It's okay. So the next one, give an expression for a solution of the system. It's okay. Ax b, if B is this matrix. It's okay. So our system, this one, Ax is B, and also we know that A is determinant not 0. Determinant not 0 means there exists a invertible matrix. So means you can use the inverse matrix. So take the disequality, multiply by the inverse matrix both sides. So we obtain A inverse Ax is equal A inverse times B. And we know that, and the matrix's associativity is valid on matrices. So, and this one, parenthesis, it's not important. We can write then this one, associativity, right? And this one. So we know that A times the inverse matrix or inverse matrix times A always identity matrix, because definition of the invertible matrix, inverse matrix. So this one is identity matrix X. So we know that this product is X. So we obtain X. X is a solution of our system, the inverse times B. So this one gives the formula to find the solution of the system. It's okay, this one. So how to find the solution of the system? And if our system this one, A-axis, and use a different color will be better. If our system this one, if our matrix is determinant non-zero, our matrix is invertible, so using the inverse matrix, so solution is this one. So how to find the solution? Write the coefficient matrix, find the coefficient inverse of the coefficient matrix, and then multiply by the b, and so this one gives the solution. It's okay. This one gives another method to find the solution of the linear system, but this one is a special system because a coefficient matrix should be square matrix and also invertible matrix. It's okay, and it is matrix, and then this one gives another method. It's okay. Any question? Okay. So the next question, can linear system A-axis B have the more than one solution? More than one solution. Yes. Any idea and this one answer about answer? And look at these and the system A-axis B. And it is possible to get the more infinitely many solution of this system. It is not possible because what is the reason? This one has unique solution, and unique solution has a unique solution. And what's the solution? X is the inverse of A times B. It's okay, this one is because A is the fixed matrix, invertible matrix because determinant not zero. So the inverse matrix is unique. And also, and here B is a unique. So, and this product is unique. A times the inverse A times B is unique. So X is unique. It's okay. And has a unique solution. And what is this solution? This solution, this one. It's okay. So this one is there exists inverse. Of course, there exists inverse because the determinant non-zero. The next question. Determinant non-zero using the theorem, and then there exists the inverse. It's okay. Any question? Okay, no question. This one is solution. It's okay. In the previous and the example. So we obtained this and the theorem. The following statements are equivalent. And so the following statements are equivalent. First one, determinant not zero. If determinant not zero, A is non-singular. Yes, A is invertible. If A is non-invertible, non-singular means invertible, so determinant not zero. We know this one. And also, A is non-singular and invertible, so X is zero, only the solution of the AX is zero. Because what's the reason? If AX is zero, A is invertible, there exists the inverse. Multiply by the inverse, so we obtain this one. So this one gives identity matrix. This one obtains zero. X is zero. So we obtain only trivial solution. Yes. And so this one is true. If A is non-singular, so X is zero. Only solution of the R homogeneous system. It's okay. So, and the next one, the following are equivalent means, and if R and the homogeneous system has only one solution, and means this matrix is non-singular, and means there exists the inverse. It's okay, if and only if condition. So the next one, A is row equivalent to identity matrix. Yes, because A is non-singular invertible matrix. So write this one using the reduced row echelon form, and then we obtain reduced row echelon form. This one should be identity. The second part gives the inverse matrix. Is okay? We know and this one. So A is row equivalent to the identity matrix. Yes. So what can you say about the linear system? Not homogeneous. It's okay. Not homogeneous. So, and take this system. It's okay. Take the system. Has a unique solution. And this system has a unique solution. Every matrix B. Every matrix B. It's okay. Yes. What is the reason? Take this system. AX is B. Our linear system. So, and our matrix is invertible, multiply by the inverse. So X is this one. So we obtain only one solution. Solution is this one. It's okay. Any question? Okay. This one is final and final question. It's okay. Final exam question. Previous year. It's okay. The inverse of any a matrix is given by this matrix. So use this information to find the determinant of A and adjoint matrix. This one is homework. It's okay. It is easy. So how to find then this one? If we have only the inverse of A, our aim is to find the determinant of A and adjoint matrix. How to find? Yes. Any idea? This one is the inverse matrix. Take the inverse of the inverse. We obtain A. And then we obtain, and so compute first, find the A. How to find? Take this one. Find the inverse of this matrix. So we obtain A. So compute the determinant of A and compute adjoint of A. And the first method. But you have no enough time to use this method in exam. It's okay. So this one it is not appropriate. It's okay. So next method. So what can you say about the next method? Yes. You don't have to use some method. Which one? Which way? And what is the relation determinant of A inverse matrix adjoint matrix? And we know that under this one, and we know under this one, this fact, and determinant of A, you don't have to compute the matrix A. It's okay. Sorry. You don't have to compute A because we know and this fact, this property. So we compute only this determinant. It's okay. And for example here, but homework maybe -4. It's okay. If this one is -4, first step, compute this determinant. So and use this one. So we obtain -1/4. Yes. And you don't have to compute under this one. And adjoint matrix. So how to find adjoint matrix? We know that inverse matrix 1/determinant of A adjoint matrix. So we know and have to compute the adjoint matrix, compute the A and then compute adjoint. But this one it is not useful. And use this and the formula. Solve for adjoint matrix of A, and this one is determinant of A times the inverse. So means we know and this one scalar, and multiply by this scalar and our matrix, and here -1/4, and means multiply all of them. Multiply -1/4, -1/2, minus 5/4. Plus 3/4 plus 2/4 This one is plus 1 over 2, and so on. It's okay. Plus 1 over 4, and we get this one. It's okay. So this one is a joint matrix. You don't have to compute the A. It's okay. Otherwise, and the first and the compute A, and then compute adjoint, and then compute determinant of A, but you don't have, maybe we have no enough time in the exams, okay? So, and the critical and the point here, if you have some properties, some and the some theorem and corollary use and this one, so we obtain the result. It's okay, easily we obtain the result. It's okay. Any question here? Okay, but this one is homework. It's okay, homework. So, and solve and this one. It's okay, fine. Inverse our matrix is this one, invertible matrix, and if inverse this one, find the determinant of A adjoint matrix. It's okay. Of course, use this method. You don't have to compute the A. It's okay. Yes. And the next method to find the solution of any linear system, but and the coefficient matrix 3 by 3 and should be 3 by 3, and this one is Cramer's rule. It's okay. Cramer's rule. What's this rule? It's okay. So, and we have 3 steps. Our aim but and sorry, not 3 by 3 and n by n, of course, and these and the first example for 3 by 3 is okay, but and these and the rule is valid n by n coefficient matrix A if our system is AX is B, our linear system. A is coefficient matrix should be n by n, critical point this one, and also and our aim is to find the X using the Cramer's rule, but and the next critical point, determinant of A should be non-zero. Otherwise, if determinant 0, not applicable. It's okay. Be careful. It doesn't work this one, and then you have to use the Gauss-Jordan reduction to solve this one. And take this system n by n, this one, so and compute the determinant of A. Maybe determinant of A is a scalar. It's okay. This one is 0 or not 0. If 0, use the Gauss-Jordan reduction. And this one, yes, this one is not 0, means we can use the Cramer rule or Gauss-Jordan reduction. But if this one is 0, Cramer rule doesn't work. It's okay. Be careful. So, yes, what's this rule? And the first, our system AX is B, but first of all, n by n coefficient matrix, and also compute the determinant of A. Determinant of A should be non-zero. It's okay. If non-zero, have to find the unknown, every unknown xi, determinant of AI over determinant of A. Determinant of A coefficient matrix, the determinant of the coefficient matrix. So what's the A sub I? A sub I is a matrix, and this matrix can be obtained from A by replacing the ith column by right-hand side. It's okay. So this one gives the solution of the unknown. It's okay. To see this one, how to apply, it's okay. To understand this method, let's give a simple example. It's okay here. Consider the following system. It's okay, this one. Let's solve this system. And the first method, write A and the right-hand side and using the elementary row operation. And then we opt Gauss-Jordan reduction or Gauss elimination. This one is first method. But here, and if it is possible, let's use the Cramer's rule. It's okay. So first of all, our coefficient matrix should be square. Look at this one. This is, sorry, any question? No question? Okay. And look at this system. This system contains 3 equations, 3 unknown. So coefficient matrix square, coefficient matrix 3 by 3. Yes, it's okay. And the first one should be square. The second one, determinant of A should be non-zero. Yes, look at the coefficient matrix A. What's the coefficient matrix? First row, coefficient of the first unknown. The second column, the coefficient of second unknown. Coefficient of the last unknown will be last column. Yes. So let's compute to this one. It's okay. Let's compute to this one, and also using the more zero here and using the first column expansion. So our aim is to get 0 here, 0. How to get 0? It's okay. Using the second row, multiply by 2 to get 0 here, to get 0 here, so multiply by 2. It's okay. So apply these operations. So we obtain the second row stays the same, 1, 2, minus 1. Apply this one. Take the second row, multiply by 2. 2 minus 2, 0. 2 times 2, 4. 4 plus 3, 7. Minus 2 minus 1, minus 3. And the next one, multiply by 2, 0. 4 minus 1, 3. Minus 2 plus 1, minus 1. Yes. So we obtain 0, 1, 0 column. Yes. Using the first column expansion. So sign of position. Plus, minus, plus. And minus. Entry 1. So minor. Determinant of the minor. 7 minus 3. 3 minus 1. Yes. So we obtain the result. Yes. This one gives minus 7 plus 9. So we obtain minus 2, not 0. So yes, applicable. Cramer's rule applicable. We can use the Cramer's rule here. It's okay. So, and the solution, let's find the x1, x2, x3, all unknown. It's okay. So look at let's come back. We claim that this one gives the formula for each unknown. It's okay. So x1 and the formula xi, a sub I, determinant of this one, determinant of a. So what's the end of this matrix? A sub I. Look at the coefficient matrix, this one, and the index number II. So x1 and the first row, this one, first row, and will be right hand side replaced by B, right hand side. So 1, 4 minus 3, the others the same. It's okay. So we obtain the A sub 1, this one. It's okay. So let's compute this determinant. How to compute? Our aim, for example, look at the last column. Last column, it will be easy to get 0, 0, 1 using this 1. It's okay. Multiply by 1, multiply by 1. Take the last row, multiply by 1, add to the first row, add to the second row. It's okay. So minus 3 plus 1 minus 2. Minus 1, 3, 2, 1, minus 1, 0. It's okay. So the next operation, take the last row, multiply by 1, add to the second row. Minus 3, 4, 1. 2 minus 1, 1. Minus 1, 1, 0. So we obtain this one using the column expansion. So sign of position plus minus 1 over 2 plus entry 1 times the minor, determinant of the minor. It's okay, this one. So we obtain this one 2. What's this one? This one is determinant of A. It's okay. So x1 is 2. Now we get the x2. What is the x2? x2 is a sub 2, determinant of a sub 2, determinant of a. Determinant of a 2 minus 2 minus 1 over 2 times a sub 2. A sub 2 means take the xi, x and use a different color will be better. Sorry. xi sub index means look at the coefficient matrix. This one is the coefficient matrix here. Take the second column because x2. Second column will be right hand side. Sorry. Right hand side. It's okay. This one. This one. So, and the first row, first column the same. The second column will be right hand side. The last column same. So we obtain this one. So using this operation to get 0, 0, 1, yes, only 1, 2 by 2 determinant. So we obtain x2 is 3. And the last one, x3 is equal a sub 3 over determinant of a. Determinant of a 1 over 2 minus. So a sub 3. First row, first column the same. Minus 2, 1, minus 2. The second one the same. Because look at the coefficient matrix. Coefficient matrix x3 for x3, right hand side should be third column. 1, 4, minus 3. And yes, we obtain this one. It's okay. The result of the unknowns. It's okay. X3 is 4. It's okay. Any question? So we claim that x3 is x1 is 2. Look at let's come back our question. Solve this and system. So Cramer's rule applicable because determinant not 0 is okay. X1 is 2 here. Yes, x1 is 2. X2 is, yes, x2 is 3. x3 is 4. I hope, yes, 4. So we claim that this one is a solution of the system and also unique solution. It's okay? Because what's the reason? Because determinant not 0 and the D system AX is B. If determinant not 0 multiplied by the inverse, so X is the unique, the inverse, this one is the solution. And Cramer's rule also gives the unique solution because the determinant not 0. It's okay? This one is the unique solution of the system. So how to check that this one is true or not? Right, substitute the value of xi and then, for example, x1 is 2, and x2 is 3, 4, minus 4 is 1, yes. Substitute here 2, 3, minus 4, yes, true. 2 minus 3, minus 2 times, plus 4. It's okay. So we obtain minus 3. Yes, true. It's okay. Any question? No question? Okay. And let's stop here. It's okay. Maybe in the next day we will give some more examples, okay, about and the system determinant, how to find the solution of the system, how to find the inverse matrix, how to find compute the determinant of A. It's okay. Now let's stop here.